Today we are going to talk about thin airfoil theory. Just by way of warning, this will be a bit long relative to some of the other videos, but it's not really a good place to break it up. The idea here is that we are going to build on what we discussed with potential flow, but now we want to start solving arbitrary geometries. In this case, we'll look at airfoils. Next time, or in one of the subsequent lectures, we'll discuss an approach where we don't need to make any simplifying assumptions. But in this case, we're going to make several simplifying assumptions that will allow us to come up with some analytic solutions. That'll be powerful because we can get some general insights from analytic solutions as opposed to specific cases for a numerical one. Of course, the numerical ones are really great. And of course, what we use on a computer nowadays to look at a specific geometry, but there are still some good insights that we can get from thin airfoil theory. So this is worth going through in detail. I'll also kind of introduce us to some of these topics. So get started. Let's just look at an airfoil. And just to get the nomenclature, we're going to define two curves. One defines the upper surface and one the lower surface. And this can be any arbitrary geometry that we want. If you haven't seen an airfoil before, C is the chord, which is a straight line from the leading edge, frontmost position, to the trailing edge. Okay, and that's called the chord. Thickness then is simply, we'll use the symbol T. By definition, it's the upper minus the lower. Whereas the camber is the sort of midpoint of the airfoil. It's halfway between the upper and the lower. Okay, so that's what's called the camber. Sometimes when we say thickness or camber, we actually mean the maximum thickness or the maximum camber. And especially with thickness, that's what we usually mean. So when we say an airfoil is 12% thick, we mean that the maximum thickness relative to the chord is 12% or 0.12. But for our purposes here, we're interested in distributions. So I could define the airfoil either way in terms of upper and lower, or more typically, we'll kind of define in terms of thickness and camber. That'll be useful for our derivation today. Another sort of preliminary is that we're going to review what we talked about with the source and vortex and extend it. So remember, we discussed the idea of a point source. This is the potential function where lambda is this constant that I can choose. That's the strength. And if I take the derivatives in x and y, that gives me the u and v component. So we're just going to do just 2D for now. But a point source and a point vortex, they're a bit limiting in what I can do. What I really want is something that's more continuous. So we're going to define a distribution of sources, and we will define Q as the strength per unit length. So this is the same concept you would have seen in a statics class, for example, or structures class, where you defined a distributed load, which was a force per unit length. So we're moving from say a point force to a distributed force, in this case, a point source to a distributed source distribution. So in other words, if I was to take some small infinitesimal chunk of this, the delta lambda, and of course I've drawn it way bigger than an infinitesimal chunk, would be Q times ds, right? Because Q is the source strength per unit length, so I multiply by some infinitesimal length, and this gives me some infinitesimal contribution to my source. So I can then do all of these same things here, right? So my potential function now is no longer lambda, right? Lambda is Q ds, so I need to do an integral. I need to integrate from 0 to c, integrate across my chord line. So this could be any arbitrary line or shape. It could be a path in general, but for our purposes, we're going to put it along a straight line along the chord. So our potential is an integral from 0 to c. I'm going to pull this 2 pi out front. So I've got 1 over 2 pi. The natural log of r is going to stay there. And lambda, remember, is now Q times ds. So I'm integrating. So Q, I'll just write explicitly, that's a function of s. And we integrate along the whole thing. Okay. Similarly, I can get u and v going to do the same thing, but we're going to have to be a little careful here because I need theta and r, for example. I need to express these. I do need to express r, but we'll leave it like that now. But I want to express things in xy coordinates. So let's imagine, let me just draw this whole thing again. We're going from 0 to c. Let's just draw, I've got this little tiny chunk, this infinitesimal chunk of source, and I want to compute the contribution of that source at some arbitrary point xy. Okay, this is the point where I want to evaluate my velocity at. So when I do that, I want to compute what is my velocity at some position xy. Well, again, we know we're going to have to do an integral. Right, so I'm going to pull the 2 pi out in front again, 1 over 2 pi. And this lambda, right, became d lambda because we're integrating, so q ds, so that's also going to be here. So I've got q of s ds. And now I got to deal with these two terms, cosine of theta and r. Okay, so what is r? Well, r, we might think at first it's just x squared plus y squared, but that's not quite the case, because remember x here, we're evaluating x from, here's 0, right? So this distance here is x, this distance here is y, but the distance I need is the distance from the center of the source to the point I'm interested in. And the source I'm interested in is going to change. So what I really need is I need to add a new variable, which we're going to call s. This is just going to be a dummy variable of integration. It's the same one we used here. And so s will vary along here. And so the distance r is actually x minus s, right? That's this distance here is now x minus s, okay? So r has become x minus s squared plus y squared square rooted. But I also have a cosine of theta. And so theta, if we go back to the source, is this angle here, right? It's the angle from my horizontal, and then this r vector that goes from the center of the source to the point I'm interested in. So the cosine of theta is x minus s divided by r. So I've got a x minus s on top, and then a second r, right? Because cosine of theta is x minus s over r, but I already have an r in the denominator, so now I have an r squared. So that leaves me with x minus s squared plus y squared, okay? V, very much the same thing, 1 over 2 pi. Notice everything is the same except for sine of theta, so that's going to give me a y over r. So this is going to look the same. I have a y ds, and then I've got my r squared on the denominator. Okay, so that's it. All we're doing is we're kind of extending our tool bag here to say I don't have to just use point sources and point vortices, but I can have a distribution of sources and vortices. And because it's a continuous distribution, I can then create kind of arbitrary shapes, continuous shapes of whatever I want. We're gonna do the exact same thing for a vortex. We'll do this a little quicker because it's the same. Remember, this is a vortex. Point vortex has this potential where circulation gamma is its strength. Here are the velocity components. We will now have a vortex distribution. Its strength per length we will call lowercase gamma. And so we'll do the same thing here. Potential now is minus 1 over 2 pi. And I'm just using this formula here. Integral of lowercase gamma times theta ds, right? And I integrate from 0 to c. And my velocities are going to look very much the same, right? 1 over 2 pi, integral from 0 to c. I've got gamma. And notice that if we flip back and forth, this looks almost exactly the same except for the sines and cosines switched, and I have a negative sign here, but it's exactly the same. So I'm just going to kind of skip to the answer here because derivation is exactly the same. ds, and then the velocity is over 2 pi 0 to c gamma of s, and this is a minus sign on this one. X minus s over x minus s squared plus y squared ds. So again, what we've done is we've allowed ourselves the ability to compute the velocity components at any arbitrary point in space that is created by this entire distribution of vortices. All right. So with those tools in place, let's now look at an arbitrary airfoil. And recall that we can use superposition. So it's going to be convenient to think of the flow field around our airfoil as being something due to the free stream, as if there was no body, just the free stream, and then something that accounts for the thickness of the airfoil, and then something that accounts for the lifting parts, the angle of attack and the camber. Okay, and if we think back to what we discussed with potential flow, we have a solution for free stream already. Thickness, if you recall, we could use a source and a sink, which is a source with negative strength, to generate an oval, right? Or if we put them together to make a doublet, we could do a cylinder. This didn't have any lift, it just modeled the thickness. And that kind of makes sense if you think about a source distribution. It's pushing things away top to bottom. Sources make sense to model the thickness of a body. Whereas if we only have sources, we will never have any lift. Or the sources don't generate any circulation, so we won't have any lift. So if we want camber, which creates lift, or angle of attack, which creates lift, we're going to have vortices to model that component. So we're going to use vortices to model the camber and angle of attack component. Those are used to generate the circulation and the lift. So here's that pictorically. We're going to have a free stream. We already know the solution to that. Thickness, we're going to do a distribution of thickness, and we already figured out the potential for that. And for camber, we'll use a distribution of vortices, which has this following potential. All right, so we have our equations. All we really need now is a boundary, or just to satisfy boundary conditions, and we have our answer. So one boundary condition is that far away, the far field boundary condition, we need all of our velocities to go to just the free stream. Well, if we look back at these velocity components, and we can remember from sources and vortices already that all of these velocity components have a 1/r term, right? So as I go very far away, my sources and my vortices, their contribution goes to 0. So all I'm left with is the free stream part, which is exactly what I want. So the far field boundary condition is satisfied automatically. So the only one I need to satisfy explicitly myself is the geometry of my airfoil. In other words, I need to satisfy flow tangency. It's not a no slip condition because this is inviscid. Essentially, we're modeling the airfoil shape just outside of the boundary layer. So we're assuming that's very thin. But I need the flow to not have any normal components. So it's only tangential. The velocity is everywhere tangential to the airfoil, nothing going normal. So the velocity has no flow through normal to the airfoil. To do this, I guess we could say it this way. This slope is dy dx. That's the slope of my airfoil. I need that to equal the slope of my velocity vector, and that has components. If I was to write this in terms of two components, u and v, right? So this is equal to, that slope is v over u. Okay, and so y, I could write, this is y, right? I have that. If I wrote it in terms of my mean camber line and thickness, which will be convenient, I could say the upper surface is my mean line, and these are functions of x, right? Plus half the thickness, just by definition, whereas the lower surface is my mean line minus half the thickness. So if I plug those into here, then dy dx is dy bar dx, and I'll just drop the function of x. Plus or minus, depending on if I'm on the upper or the lower surface, 1/2 times the derivative of the thickness. Okay, so that's my boundary condition. And now I have everything I need to solve this problem. In theory, I've got an equation for u and v, right? I can compute u and v. We already figured those things out. So I can compute them at a bunch of points along my outer boundary. And I just need to satisfy this boundary condition given the inputs of what my geometry is, right? What's the camber and thickness of the airfoil that I'm interested in. And we'll do something like that next time. We'll have to do that numerically for an arbitrary shape, but this time we want to simplify things a little bit so that we can get an analytic solution. Again, analytic solutions are powerful because while they're not as good for a specific case, they're good at getting sort of general behavior, helping us to understand what factors matter, what the contributions are in a general sense. So we're going to add a few simplifications here. And this is where the thin part of thin airfoil theory is going to come in. And I want to emphasize that all of these approximations we'll only do in the boundary conditions. So later when we regenerate flow fields, we calculate velocities, we calculate pressures and forces, we will not use these simplifications, but we will do that just to do the boundary condition to solve for what the source and vortex strengths need to be. Okay, so the first thing we're going to do is my full boundary condition, right, is just writing it again, is that dy dx is equal to v over u. And v over u, as we've broken it down, is v infinity sine alpha, my free stream component, right, plus v from my thickness plus v from camber. And these are the solutions we found before, right? This is the camber portion, and this is the thickness portion from the sources. And then for u, I've got the free stream part, and then I've got u from thickness and u from camber, or in other words, u from sources and u from vortices. That's the full boundary condition, but that's going to be too hard to solve analytically. So we're going to do a few things. First, we're going to assume that the angle of attack is small. Actually, this one is not necessary to do. You can actually solve thin airfoil theory exactly without doing this, but I'm going to do it because it's commonly done and it's just going to save me a little bit of writing, but you don't need to do this. So in that case, we're going to assume that cosine of alpha is about 1 and sine of alpha is alpha. Okay, small angle. Again, you don't actually need to do this. And you can completely solve everything. It's not any harder. But these next two we do have to do to solve this. And one is that we're going to assume that the free stream velocity in the x direction, so we're looking at this part here, we're going to assume that this term here is much bigger than these. And this is part of that thin part. So if my airfoil is thin, we're going to assume that it's not doing much in the x direction, but all of the disturbances are primarily in the vertical direction. So we're going to ignore these terms, not in the only in the boundary condition. We're not going to assume they're 0. Eventually we can compute them and they will be important and they will alter the pressure. But just for imposing the boundary condition, we're going to assume that this term is bigger than these. Okay, we're not assuming they're 0. They're not, but they're just much smaller than this. Okay. The last thing we're going to do is that, whoops, sorry, turn that off. Is that we're going to, well, let me write this out, what we've done so far. I'll just write exactly what we did so far. If we go back, a bunch of terms were gone. So we're going to say v infinity, and remember we simplified alpha plus vt plus vc. And on the bottom, we have just v infinity, because we're assuming that one is small. And this equals dy dx, but I'm also going to write dy dx this way. Okay, I'm going to write that out. So we have dy bar dx plus or minus 1/2 dt dx. Okay, this is what we've got so far. The last simplification that we're going to make is that we are going to apply this, and I guess I could simplify some further. We're going to not use the slope. Well, let me back up. Here's my airfoil. Okay, here is my slope at some point, and here's the chord line, which I totally didn't hit the trailing edge, but let's pretend I did. I'm going to use the exact slope, but I'm not going to compute the velocities at that point. I'm going to compute the velocities at the chord line. So I'm going to do all my integrals along the chord line. I will use the correct slope, but I will project it down to the chord line. And now I will still do the upper and lower surface. So I'm going to project everything on top to, let's say, some epsilon above the chord line, and everything below, I'm going to solve just some epsilon below. So I'm still going to use, again, the right slope. So I'm not going to pretend like this is flat. I'll use the right slopes, but the corresponding velocities that I compute, I'll compute just barely above and just barely below the chord line. So in other words, if I rearrange this equation here, I'm going to take this and move it over. I'm going to move this over. So I'm going to just have these guys left. So I'm going to compute those velocities at 0. Okay, I'm going to compute these at y equals 0, not where they actually are. They're actually a little bit above, but we're going to assume things are pretty thin so that these velocities are pretty close, even if I just compute them just barely above, is equal to, let's see, so I'm going to move this over. So I've got V infinity times, there's a minus alpha now since I moved that over, plus all the rest of the stuff. Okay, so those are my simplifications so that I can get an analytic integral here. All right, so notice what we need to do. I actually only need a couple things. I need these velocities, the V components, but I need them at y equals 0. I don't want them at some arbitrary point, which we derived earlier. So let's simplify that. Here's what we derived for sources. We figured out for the sources at some arbitrary location, x and y, what are the velocity components. Now we need to figure out what happens as y goes to 0. And recall that we actually only need the V components for this boundary condition, but eventually we're going to want both. So I'm just going to do both. And in fact, once we do both, it'll be easier to do the Camber one. So let's start with the easy one. This one is easy, the U one, because that just disappears. And so one of these cancels with that one. So U of x, and now we have just y equals 0, is 1 over 2 pi integral of q of s divided by x minus s ds, right? So it's simplified. This one is harder because I have a 0 on top. So we could say, well, it's 0, but it's actually not 0 everywhere, right? Because this is 0, this is 0. But at the point where x equals s, then this denominator is also 0. So I have a 0 over 0. So it's not clear what that evaluates to. I'm not going to derive it right now. I do it in the book so you can see it, but this does turn out to be a finite integral. We have to do like a change of variables, expand our limits, and we can actually evaluate this. But what we'll see, this is going to be 0 everywhere except for when s equals x. So this s is going to become an x, and then now it's not dependent on s, so we can pull it out of the integral. And the result is, when we do this evaluation at y equals 0, it just is plus or minus q of x over 2. So the plus corresponds to the just barely above y equals 0, and the minus is on the bottom side. Okay. So that's it. And we should expect actually that this velocity is discontinuous. If we look at what we're modeling here, the u velocity seems like it should be continuous as I go from above to below. But the v velocity, if I'm just above, everything is pushing me up. But if I'm just below, everything is pushing me down. So it's not surprising that there's a discontinuity as I cross that y equals 0 line. All right, Camber looks almost exactly the same. Remember that the same integrals, but they're kind of flipped, or they're kind of reversed, except for one has a negative sign too. So let's just skip to the answer here. Same process. For y equals 0, this is plus or minus gamma over 2. And the V1 has a minus sign in it, so it's minus 1 over 2 pi. And this is going to be gamma over x minus s ds. Okay, so that's it. So now I have the terms that I need. I can put them in this boundary condition. So let's write all that out right now. So we've got, well, actually, I'll just write exactly what we had before, just so I can remember. We had Vt plus Vc evaluated at y equals 0 is equal to V infinity times a minus alpha plus dy bar dx plus or minus 1/2 dt dx. This is what we already derived. Now we just computed Vt and Vc. Right, this is Vc and this is Vt. We computed them at y equals 0, so let's plug them in. The Vt part gives me q of x over 2, and there's a plus or minus on that. And then the Camber part gives me actually a minus sign. Let's see, it's this one right here, minus 1 over 2 pi times the integral of gamma x minus s ds. Okay, so remember what we were going to do. We wanted to associate the sources, which is q, with the thickness part. So we're going to do that. We're going to equate this term here with this part here. And remember, there's a V infinity multiplying all of this, so it also occurs in this term. Whereas the vortices, we're going to equate with the lift part, so camber and angle of attack. So this stuff here, we're going to equate to this part here. Okay, so if we do that, notice this plus and minus is the same as this plus or minus, so the signs are going to be the same. And there's a divided by 2 on both sides. And remember, I need to put that V infinity over. So if I do all that stuff here in one step, I get Q of X equals V infinity times dt dx. And that's pretty nice. So let's say, look at what this tells us. That says, given V infinity and my thickness distribution, which are things I should know, right? You have to tell me what airfoil you're using. All I need to do is take a derivative along my airfoil of that thickness distribution, and this tells me directly exactly what source strength I need. So I know my distribution of sources. I just create them based on the derivative of my thickness distribution, and that'll recreate the right flow field around an airfoil of the thickness that I want. So if I have no lift, pretty easy. I can create any shape I want that has no lift, just thickness. At least within the assumption of thin airfoil theory, by just taking the derivative of that shape and making my source strength exactly equal to that. The lift part is a little bit harder, so that's in red, so we can equate those two terms. I'm going to bring the negative sign over to the other side, so I've got 1 over 2 pi integral of gamma over x minus s ds, and I brought the negative over here, so I'm going to distribute it throughout. So I get alpha minus, I change the signs here, dy bar dx. Okay, so this one's a little harder. Recall what I want to solve for is gamma, but I can't do that explicitly yet because this is an integral equation. I don't know what y bar is, so this one doesn't simplify quite as nicely. So let's take it one step at a time. Let's do the easiest case, which is let's do a symmetric airfoil. If it's symmetric, which of these terms goes away? Well, if it's symmetric, I have no camber by definition, right? So this term is 0. Okay, so there's no y bar is 0, right? It's symmetric, so the derivative of y bar is 0. So this is gone. So I'm going to bring the 2 pi over. I still have this term, but that's all. So let's write that again. So what I've got for a symmetric case is I've got the integral of gamma x minus s ds equals 2 pi. Let's see, so I've got the 2 pi and I've got v infinity alpha left. All right, so this is getting a little better. There's some hope that I could integrate this because there's, the only thing that's unknown here, this parameter is just alpha, and it's just, a constant or a scalar here. I don't have some distribution. So this seems like something I could potentially integrate. To do it, we're going to use a coordinate transformation. It's going to be one that we're going to use multiple times. It's a cosine transformation. And it's going to look like this. So we're going to say x is going to be c over 2 times 1 minus cosine theta, where now theta goes from 0 to pi. So notice when I plug in 0 here, cosine of 0 is 1, so this whole thing goes to 0. And then when I plug in pi, cosine of pi is minus 1, so this is 1 minus minus 1, which is 2, which cancels that, so I go to c. So in other words, instead of going from 0 to c, I'm going from 0 to pi. The reason why we're doing this is going to make the integral easy, but this is a common trick that's used in aerodynamics for spacing. Is what happens is if I've got, say, something that I'm spacing uniformly from 0 to c, of course it looks like that. But if I space uniformly from 0 to pi and then do this transformation, it'll look something like this. It'll bunch them up closer to the front and the back. So they'll be tightly spaced on the ends and then spread out towards the middle. Kind of like how the cosine function gradually changes the top. Things are going to be tightly spaced if you think about the projection of the cosine, and then they start changing rapidly in the middle. This is used a lot for things like airfoils and wings, where let's say on an airfoil, a lot of my change happens at the front and the back. So I want to tightly discretize. Same with a wing, like a lot of things will happen at the wing tips. And so I want to change my discretization. That's not why we're doing it here. That's just, by the way, something we'll also do later. When we go to evaluate wings later, we're going to use the same transformation. S, same thing. I need to give it a different symbol though. So we'll call it phi. Okay. And I also need a ds here. So let's just take that derivative. ds is the first term is constant. Derivative of cosine is a minus sign. So that's going to cancel with this minus. So I get c over 2 times sine phi d phi. And my limits of integration are for s, and s is going from 0 to pi now, right? Instead of 0 to c. So if I plug all that in, I change my integral. This becomes the integral from 0 to pi. I now have gamma, which is now a function of phi instead of s. X, I'm going to do all this in one step. So if it doesn't make sense, write it out yourself and you'll see. But x has a c over 2 in it, s has a c over 2 in it, ds has a c over 2 in it. All of those are going to cancel. And I have x minus s, so I have this term minus this term. So when I subtract, I get 1 minus cosine theta minus 1, so those cancel, plus cosine phi. So I'm left with is cosine phi minus cosine theta. And then from the ds term, remember the c over 2 already canceled, so I'm left with sine phi d phi. Sine phi d phi. And then on the right-hand side, I still have everything that's left over from here. Okay, so again, the only reason why I did this is going to make it a form that there's a known integral for. All right, so yeah, you can, if that was too many steps at once, just make those substitutions and you'll see it simplifies to this. All right, so let me repeat that. Same thing again. Same thing we just got. Gamma of phi sine phi cos phi minus cos theta d phi equals 2 pi v infinity alpha. Okay, so here's an integral. We can go look this up on our integral tables. It's useful. We're going to use it again later in the semester when we talk about wings. This formula holds for any n, any integer n. What two cases are useful to us right now. One is the case n equals 1. So if I plug 1 in here, I get this thing on the left-hand side. And on the right-hand side, I get sine theta over theta, or over sine theta, those cancel. And I'm left with just pi. Okay. The other case we'll look at is n equals 0. This becomes the cosine of 0, which is just 1 on the left-hand side. The sine of 0 is 0, so this whole right-hand side goes to 0. All right. So let's look at that. And the integral that I want, it looks very similar, right? This denominator is the same. But I want a cosine on top. I've got a sine on top. I have a pi here. So that's great. So I could see that if I chose my gamma to be, I need this 2 pi alpha. I need this constant, right? If I put the 2 pi alpha there, it will come out and be equal to the right-hand side. So that's great. Not 2 pi alpha, sorry. I want the pi. 2 v infinity alpha. The pi I want to come from here. So I need a cosine on top, but I've got a sine on top. So I can multiply by cos phi over sine phi, right? And notice if I do that, again, this constant comes out front, cancels with those, so that's great. So I'm left with pi. And if I've got cos over sine, the cos stays here, the sine cancels with that, and that's exactly this integral, which integrates to pi. So that all works out, okay? So that tells me a solution for my vorticity distribution. Unfortunately, that's not at all, because if we look at this case here, notice if I now add another term, let's say I add, let's add k over sine phi, where k is any arbitrary scalar. Okay, the k can come out, and if I have sine phi, it cancels with this one. So I have 1 over this thing, which is exactly this, integrates to 0. So the integral of this thing gives me the thing I want plus 0. So this is still a solution to this equation. So yes, I could choose k to be 0, that works, but I could choose k to be anything. So my general solution is this, which is troublesome. It tells me I can get an infinite number of solutions for my vorticity distribution, and they will all satisfy my boundary condition that I need. That's a problem because I can get any circulation that I want now. So which one is the right solution? In some sense, actually, we shouldn't be too surprised that this happened, because recall that what we're doing is we're solving this irrotational flow field where if I took control volumes anywhere, the circulation is zero everywhere. By definition, right, it's irrotational. The only way I get some net circulation is if I choose a control volume that goes around my singularities, and that's going to give me the lift. But I have to specify that. I have to know how much lift I'm going to generate, because I'm only right now solving for this flow field where everywhere is irrotational. So I need some way to figure out how much circulation I need. This is kind of related to what's called D'Alembert's paradox. We haven't really discussed that, but I'll just briefly share that in potential flow, I can get any number of solutions. So I can get a solution like this, I can get a solution like this. And in all of them, the drag is zero. And this will still be true. We won't resolve this. This is actually true for potential flow. If I solve for my pressures and I integrate around it, I always get that the drag is zero. And that, doesn't make a lot of sense. This, leads to the idea that, okay, if I'm in the water, which is very well approximated by potential flow, it's incompressible and very, very well approximated by incompressible and viscid, that I should be able to take a boat and just give it a little push and it should just keep going, which of course doesn't happen. The reason for that is that if I just introduce just the tiniest bit of viscosity, then a solution like this is unphysical, right? Then I will have this unsymmetric case, and I should have, this is the physical solution I want, but potential flow says any of these are possible. I don't know which one it is. And this is not possible with any viscosity because I have such a huge velocity gradient. The shear stresses would be enormous. The boundary layer flow is in no way going to be able to, or the flow near the body is no way going to be able to navigate such a huge velocity gradient without separating. So I need some way to impose this. Potential flow won't do this automatically. So I need to impose this somehow. One simple way we could think about this is if I go back and I look at what the velocity is at the trailing edge from my vorticity, it looks like this, right? Plus or minus gamma over 2. So for a lifting body, if I look at what's happening at the trailing edge, and again, imagine again, we're looking at thin airfoil, so I really should model this as a line here, right? Just above, we're saying the velocity at the trailing edge is gamma at the trailing edge over 2, whereas on the bottom side, it's minus gamma over 2. That isn't physically possible, right? Because that means I've got this discontinuity in the velocity, which I shouldn't have. There's no geometry there to support that once I get past the airfoil. So the way we're going to satisfy this is we're going to say that this only works, this can only be physical if gamma goes to 0 at the trailing edge. Or in our coordinate system where we're doing it from 0 to pi, that means gamma at pi is 0 at the trailing edge. Okay, this is what's called the Kutta condition. There are other ways to derive it, but this is one simple way we can motivate this. This is going to allow us to, of all the infinite possibilities, there's K, could be any number of things. This is going to tell us what the right K is to give us this kind of physical behavior where there's not this sharp curvature and infinite velocity gradient. So we had to impose this because potential flow won't make this happen naturally. This still won't resolve the drag being 0 thing. This will still happen. The drag will be 0, and that should for potential flow. So we have to have other ways of predicting drag, but it'll be useful for getting pressure distributions and lift. Later in the semester, we'll talk about ways that we can get drag. So let's go back now. Go back to this formula and figure out what K should be. So I'm going to write that same expression again. So gamma, I'm just going to write here as a function of theta. It was 2 v infinity alpha over tangent theta. Let's see. Yeah, this part, I'm just going to write this as tangent. I'm just switched from theta from phi to theta. It doesn't really matter here. Plus some arbitrary k times sine of theta. And now I have this additional condition that gamma at pi must be equal to 0. All right, if I plug pi in directly, this is 0, so I have something over 0, which is bad. And this also is 0, so I have something over 0. So this blows up. So that's bad because I need it to be equal to 0, not infinity. So if we look at this, the only way that's going to we have hope for that to work is if it's 0 on top and bottom. And I've already got, this is a sine over cosine. So I've got a cosine over here. So if I can get something that's cosine of pi is -1. So I want like a 1 over here. So the way to do that is, let's say that k is equal to 2 f v infinity alpha. If I do that, then gamma is equal to, I'm going to factor this out, 2 v infinity alpha divided by sine theta. And I'm left with, here I've got a cosine. So I'm going to cosine theta, and here I'm left with just 1. Okay, so at pi, this is 0, and this is -1 plus 1. This is 0. So I have a 0 over 0. So we have to use L'Hopital's rule to see if this is going to work. If I take the derivatives top and bottom, this becomes a minus sign, and this becomes a cosine. So this is 1 on the bottom, and this is a sine, so 0. So indeed, this does work. Gamma of pi is equal to 0. So this is my solution. For symmetric airfoil, we've now figured out what vorticity distribution I need along my airfoil to give me the right flow field given some angle of attack that I want. Okay, and remember, theta is just some dummy variable. That's what we're using to parameterize from 0 to pi. We could change it back to x if we want. It was just a coordinate transformation, but we can also just stay in theta space. It doesn't really matter. Okay, we've got the symmetric airfoil. Let's go back and do the camber airfoil. Let's go back and look at our equation. Before we got rid of things, here was the full equation. Remember, we got rid of that term, but we're going to keep that term now. We did a coordinate transformation, right? Like this. We're going to do the exact same coordinate transformation again. So let me write it out again. We've got the integral 0 to pi of gamma of phi sine phi cos phi minus cos theta d phi equals 2 pi v infinity. So far, all of this is exactly the same. But now we're going to add this term b, which is our camber part. Okay, where in this case, b of theta is, it's that dy dx term, but we did a coordinate transformation. So it's now, it was a function of x, but we're going to make it now a function of theta. Okay, so again, b is just, it's that derivative of the camber, but expressed in terms of theta rather than x. And we still have this condition that gamma of pi needs to be 0. All right, so there's no way that we can get one solution because b could be anything, right? I can choose any camber distribution I want. So we need something that's going to be generalizable. And the way we're going to do that is we're going to use the Fourier sine series. Fourier series, remember, if we retain enough terms, we can represent any distribution that we want. So we're going to assume that we're going to use the solution that we already got for the symmetric case and just add to it. So here's the solution we already got. So let's assume something very similar to that. So we'll write that out, 2 v infinity 1 plus cosine phi divided by sine phi. And what we have left is the angle of attack. So we're going to write this more generally as some coefficient, which is going to obviously include the angle of attack, but may have additional terms. And then on top of that, since we have camber, we're going to just do a sine series, a Fourier series, like as follows, sine of n phi. Okay, so just a Fourier series where we need to compute all these coefficients. All right, so it's more or less the same process. I'm going to spare you the math, but we plug this in. We can use the same useful integral we had, simplify things, and figure out what these coefficients need to be. And if we do that, what happens is that we see that A0 is the angle of attack, unsurprisingly, with one additional term related to my camber line, and then the other Fourier coefficients, which I can include as many as I want, as many as I need to get a good representation, looks like as follows. Okay, so the process is as follows. You give the camber line shape, right? You have to define that. That's y bar. We take the derivative to get dy bar dx. We do a variable substitution. So now we have b, and then we just evaluate these integrals. Generally, we'll do that numerically. We'll show an example where we can do it analytically because it'll be simple, but normally we do these numerically, and we just get a bunch of Fourier coefficients. And I may have to try different numbers to see, once these coefficients start getting small and I'm not really changing my circulation, or I'm not changing my forces or things that I care about. All right, so what do we have now? We now have a solution for any airfoil, symmetric or cambered. And once I have the solution, I have gamma, and we already have Q. We got that one much easier. So since I have Q and gamma, I can compute my velocities, U and V, U and V. So I can compute my velocity anywhere. I compute it along my airfoil. So since I have velocities, I can now get pressures. And since I have pressures, I can get forces, which is what I generally care about most of all in the end, usually. Recall again, we derive for irrotational incompressible flow that Cp is 1 minus V over V infinity squared. That's not general, that's for a irrotational incompressible flow, which in our case is 1 minus, we could say, let's write it out in full. V is U squared plus V squared, but we're going to retain all the terms, right? So this is going to be V infinity plus U thickness plus U camber squared plus, actually it's not V infinity, it's V infinity sine theta. V infinity cos theta, cos alpha, sorry, plus U thickness plus U camber squared plus V infinity sine alpha plus V thickness plus V camber squared, all of that divided by V infinity squared. Notice that this time I did not make the approximation that these things are zero. And I keep all the terms because I can. It's not really hard to do it at this point. The only reason why we made that before is because doing the integrals would be impossible otherwise. So I retain everything to get the velocity. That'll give me a more accurate pressure distribution. I'm going to skip this and come back to it. Once I have pressures, I can get forces. Okay, these are not specific to thin airfoil theory. This is just simply, I know my force acts in this normal direction. And so given the slope of my airfoil, that's dy dx, I can get the components in the x and y directions, right? Same with the moment. These are just general. If I know a pressure distribution, how do I get forces? So I get those forces, I have pressures. I'm going to now do the integral, and what I want is lift and drag. So what's going to happen is, first of all, I can tell you right now that we shouldn't be surprised that the drag actually ends up being zero. You can do all the integrals, do all that math. It's going to be zero. This is what we already knew is going to happen with potential flow. There's no viscosity, and it always, the drag of potential flow ends up being zero. The lift, on the other hand, is going to have some terms, and it looks as follows. I get pi rho V infinity squared C A0 plus 1/2 A1. This is not a simplification. I did not leave any terms off. You could have an infinite number of Fourier terms, but these are the only ones that remain. And the reason why, I didn't write this out, but if you go and write this out, you'll see what happens. That these terms, right, they have all these cosines and such. And when I put this in and I start doing these pressures, right, and I put them together, because the Fourier series are orthogonal, right? So anything that's like cosine of n theta times the cosine of m theta d theta, as I integrate from 0 to pi, that is always 0 unless n equals m. So all these terms start canceling out, and this is all I'm left with is these remaining few. Okay, so let's now, since we always like non-dimensional things, let's non-dimensionalize that. That's, of course, we divide by dynamic pressure and chord. So all of this gets canceled, and this gets canceled. I get 2 pi, and then I'm going to write these things out, A0 and A1. Right, this is A0, and A1 is this stuff, except for I put a 1 here, so it's just cosine theta. I'm going to kind of do this in one step here. So write this out yourself if you want to see it more carefully, but just in the interest of time, I'm going to put these together in one step. Looks as follows: b of theta times 1 minus cos theta d theta. Okay, that is my lift coefficient. General, right? I can have infinite number of Fourier coefficients. All right, now we're to something really useful, which is recall what my lift distribution looks like. Okay, it looks something like this. We're, of course, in potential flow, not going to model this viscous part. So we're only be able to model the linear portion. But before we said, well, for a general linear expression, we could write it like this, right? M is alpha minus alpha 0, where this is alpha 0, right? This is the angle of attack. This is alpha and CL. That's the angle of attack of 0 lift. And M is just my slope, right? So if we compare this to this expression here, notice that what happens is that this kind of ugly thing is alpha 0, and this is M, which leads us to the super useful result, which is that the slope, the lift curve slope of any airfoil is 2 pi, okay? Notice this does not depend on the thickness. It does not depend on the camber. It doesn't depend on the airfoil shape at all, at least theoretically here in the limits of thin airfoil theory, that my slope is 2 pi. And that's it. That's an incredibly useful result. We use it all the time to try to estimate performance of an airfoil. In practice, the actual slope is usually a bit less. It's very close, but because of viscosity, the slope is a little bit less than 2 pi. But this is a very good approximation for real airfoils. This formula is a little bit less useful. I mean, we can use it to estimate alpha 0, but you know, it's obviously specific to the case. I need to know what the exact camber distribution is. All right, one other generally useful thing is the pitching moment. Let's see if my slides want to rotate here. Okay, here we go. Same thing, plug it in, do the math. A lot of terms cancel because of orthogonality of the Fourier series, and I'm left with just these terms. One thing that if you haven't seen on pitching moment, a term that we'll use is the aerodynamic center. Imagine I have an airfoil at some angle of attack, and I can resolve the forces any way I want, because here's the lift, here's the moment, but I could move that thing around, right? I could say, let's look at that exact same case here. And maybe I want to specify it here, right? Or I want to specify it here, right? You remember from statics, I can specify anywhere I want. Of course, what that moment is will change depending on where I specify it. Well, there's some point on the airfoil where that moment is 0, right? I can find some point where the moment is 0. That's called the center of pressure. For aircraft, that ends up not being a very useful point because it depends on the angle of attack. So if I now take that same airfoil and I put it at an angle of attack, now the lift is different. It's going to be bigger. My moment is going to be different. And so where the center of pressure is going to move around. And so I don't really like that, because then I can't say, well, here's the center of pressure of my aircraft. You say, well, what's the angle of attack? And when I change the angle of attack, which I do a lot, I have to keep moving the center of pressure around. Well, there's a different concept, which is called the aerodynamic center. The aerodynamic center is the point on the airfoil, not where the moment is 0, but where the moment doesn't change. So the moment is independent of angle of attack. So in other words, dm d alpha is 0. The moment is not a function of angle of attack. So whether I'm here or here, any angle of attack, again, the moment's not 0, but there's some point where the angle or the moment, this moment that I compute, doesn't change the angle of attack. So if we look at this expression, where would that point be? First of all, let's look at these terms. Where does angle of attack even appear in this equation? Let's go back and look at our Fourier series coefficients so we can remember. Angle of attack is nowhere here. This is camber. This is the only place. Only in A0. That's the only place where the angle of attack appears. So in other words, if X equals C over 4, if I plug that in, this term is gone. So there's no A0 here. So my moment does not depend on the angle of attack at the quarter chord. So this becomes the theoretical location for the aerodynamic center, the quarter chord. Meaning this is my chord length. If I go 1/4 of the way back, that's what we call the quarter chord. That's the theoretical location for the aerodynamic center. So if you look at airfoil tables, you always see when they specify the moment, they specify it about the quarter chord. That's because, again, that's the theoretical location for the aerodynamic center of an airfoil. By the way, if we computed the pitching moment about that point, the pitching moment, looks like something else. This is the pitching moment about the aerodynamic center. It ends up being pi over 4 times A1 minus A2. That's a little less interesting. This is a sort of critical big piece that we've gotten. Okay, so I just want to do one last example here, or not one example as we're wrapping up. Let's just do a very simple case where we can do some things analytically. Here's a camber line that's parabolic, so it's like a quadratic shape. Epsilon is just some arbitrary constant. It just helps me move it up and down. I'm not sure why I put the 4 in there. We don't need that because it's an arbitrary constant. So if I make it bigger or smaller, it just kind of changes. It's still quadratic, but it kind of changes the shape, right? So I have y. Let's just go through our steps. I need the derivative of this. So that's going to be from the first term, that's going to be 4 epsilon, and the c's cancel. And I guess that's it for the first part. So I'm going to put a 1 here. Minus, on the second term, this 4 epsilon just comes out of the whole thing, right? So this is cancels. I just have x. On this term, I've got a minus x squared over c. So that's going to be a 2x over c, assuming I did that right. Okay, so that's just my derivative. Now we do our coordinate transformation. Remember, our coordinate transformation was x equals c over 2, 1 minus cosine theta, if I'm remembering that correctly. Okay, so that's our coordinate transformation. So let's plug that in. We notice in this case that the c over 2's cancel and the 1's cancel, and actually this ends up being super easy. So b of theta, the slope of the camber line in terms of theta, is just 4 epsilon times cosine theta. Okay, so now theta goes from 0 to pi. Okay, now we have b, so we can do our Fourier coefficients. Let's plug it in here. The integral from 0 to pi of cosine theta is 0, right? So this whole thing goes away and I'm just left with alpha. And this is going to be cosine theta times this. This is going to be 0 for every case except for n equals 1, where it's going to be cosine squared. And this is a common integral. The integral of cosine squared from 0 to pi is pi over 2. So that cancels and this just becomes 1. So these integrals became really easy. So again, a0 just becomes alpha. A1 just evaluated to 1, but I have this 4 epsilon left, so I need to include that. And then A2 and onward is all just 0. Every single one of them is 0. All the rest are 0. Okay, so yeah, now I can get things like the lift. I can go back to this formula here. It's this thing, so I can get that. It's just pi rho v infinity c alpha plus 2 epsilon, or I could get CL. I divide by 1/2 rho v squared, so I get 2 pi alpha plus 2 epsilon, and that's it, right? So I'm done here. This just shows a very simple case. Again, in more particular cases, we'll do it numerically because I can't do it so easily analytically. In a general case, we'll use this again. Later in the semester, we'll use the solution from a parabolic camber as a motivating case. All right, one final thing I want to go back to really quickly. This is what's called Reigel correction. So if you do thin airfoil theory and you retain all these terms and not use the same thing as in the boundary condition and delete these, you'll actually do really well most of the time, everywhere except for the leading edge. And the reason for that is, remember, we're doing thin airfoil theory. So everything we assumed is that the disturbances are small, right? And they're mostly just vertical. There's not much happening in the streamwise direction, at least in the boundary condition. And that works very well, except for near the leading edge. Near the leading edge, there's a stagnation point. So the disturbance is not small. The disturbance is complete, right? We go from our free stream all the way to 0. So that's a complete, 100% disturbance, not small at all. And the velocity components are certainly not, in the x direction, are certainly not negligible compared to the free stream. So we'll get poor values near the nose. In fact, it'll blow up. It'll go towards infinity sometimes, unless you're at a certain ideal angle. So Reigel's correction is a simple idea. It's not really even sort of a physics thing per se, just a heuristic here, which is to say, let's say V, I'm going to call this mod, my modified velocity. It's my original velocity times the cosine of beta, where beta is, actually I should just write it out. I shouldn't have wrote beta. It's really just, yeah, let's just write it out. Beta is the local airfoil slope. Okay, so if this is my airfoil, and this is some location, this is beta, right, that angle. And the motivation for this formula is that I know at the leading edge or at a stagnation point, my velocity should go to 0. So when I get to 90 degrees, where beta is 90 degrees pi, this thing becomes 0, right? Or pi over 2 rather. Right? This is 0. So that's it, right? That's not really physics-based per se, other than to say, I know I should get a stagnation point at 90, so let's just change my velocity so that happens. And then at smaller angles, right, then this does basically nothing. So if I was to expand this, right, beta, let me draw this in terms of the variables that we're actually computing. This is beta, this is dx, dy. So the cosine of beta is dx over the square root of dx squared plus dy squared, or that's 1 over the square root of 1 plus dy dx squared. I write it that way because that's the things that we actually are using is my airfoil slope. So we could write this as v times 1 plus the square root of 1 plus, and then this is that airfoil slope, dy bar dx plus 1/2 dt dx squared. Okay, so again, it just uses things we already have. And so how you use this is, you compute velocity like we already explained. We just add this one correction. Basically, if you don't like looking at this, right, just compute beta however you like. It's just that angle of the slope of the geometry. Now we have this modified one. So when we compute our pressures, instead of using V, we use V modified. So this is going to be 1 minus V mod or V infinity squared. And that'll give you a much better pressure distribution towards the nose, and everywhere else it'll have negligible change. Okay. So that's it. And again, that you only need that if you care about pressure distributions. If you only are interested in the forces, then this never enters. Actually, pressure distributions are the hardest part about thin airfoil theory, because then you have to compute all these terms, and you kind of have to be careful about some of the singularities that can occur. All right, that's the end of thin airfoil theory. Again, to recap the usefulness, the most useful thing by far are these results: lift curve slope, location, aerodynamic center. It can be useful. I should say we don't use this very often anymore computationally, because the main motivation for this was trying to find a way to solve things that were analytic. Even though we can now do this numerically, there are better methods that we'll talk about, like panel methods, where we don't have to make some of these simplifications. So we don't typically do this very often on a computer. It still can be a useful point of comparison just to understand how well it works. But the main benefit of it by far is kind of these results we get from it, these analytic results. All right, it was a long one, but that's it. See you next time.